Hi guys, this is Yashwant Vijaykumar. I'm a senior engineering manager and architect at Adobe Experience Platform, specifically with the Unified Profile team. Today we're going to talk about massive data processing in Adobe using DeltaLake. Agenda-wise, we're going to introduce what kind of data we store and what kind of challenges we have with the representation and other issues with or without the data lake. And then we're going to talk about strategies that we use to mitigate them. And hopefully we have enough time to show some performance numbers to say what we're doing is actually working and useful. But before we dive any deeper into the architecture, I think we need to understand how the data flow looks like for our platform. So we have a lot of internal solutions and external solutions, which are piping in a lot of marketing data. You have solutions like Adobe Campaign, which is for email campaign orchestration, Adobe Analytics, it's like one of the largest vendors of analytics software in the world. So you have a fire hose of data coming in a variety of formats. The formats can be JSON, Parquet, Protobuf, name whatever you want. Now, all of this gets converted into an experience data model, or we call it XDM. So this is a standardized JSON schema tailor-made for marketing use cases and other use cases. But today, we're just going to focus on the marketing side. We use a lot of Spark to gather this data and get it into the unified profile system, which gives you a 360-degree view of your customer's details. Now, every single tenant, that is every client, has their own unified profile store. And the data from the unified profile store feeds into a fire hose of changes called the change feed, which again, you can use for streaming, statistic generation, and so on. The biggest value add of unified profile is that you can make extremely complex queries. Say like get me everybody who did a trial of Illustrator in the last 7 days, have added Photoshop into the cart, but have not purchased it yet. This is just like, touching the surface of its capabilities. It can do a lot more. But performance and magnitude of scale is kind of the things in order. At the heart of unified profile, right, is in order to give 360-degree view, we need to maintain the identity graph. Identities of personas can come from online data, offline data. The identities themselves can be anonymous IDs, like cookie IDs, etc., or known IDs, right, like email addresses, phone numbers, loyalty IDs, etc. So all of these IDs are put together in this graph generator, and we get a graph representation of the identities that we need to store in the unified profile. Now, we're going to see why this is the exact element that actually complicates the storage and the processing. To storing a graph, there are so many different ways, but storing a graph at scale is a problem of its own, and it's well researched. What we are going to try to do is we're going to dumb down the entire problem into a very simple representation that we have here on the slide. Let's take primary ID. The primary ID is the ID with which the data was generated. Let's say a cookie ID related to a click on a website. The related IDs refers to the graph edges, right? As in the graph nodes that it's connected to. The fields, field 1 to 1000, we just have a whole lot of fields and data related to the record. So you can imagine that each record in this table represents a click, and primary ID tells you who generated the click. Related IDs tell you who that ID is related to. Let's actually focus our attentions on the last two lines, which is like, so it says 789 is linked to 101. And so what you will see is we also have a row for a record that is generated by 101. And we see that the related ID is 789.101 again. So the idea is we need to keep track of the related IDs as the data is coming in, whether it can be immediately or probably after. But when we are doing the processing, that is when we need to run, reports or segmentation queries for activation and targeting, we need the related IDs field is extremely important. Now, let's assume a scenario where we get a new linkage, a new record comes something, and this causes a new linkage, and this causes a graph change as a result of that. So this record is generated by this ID 103, and it links 789 with 101 along with 1103. So this is, we don't need to focus on the fields over here, right? The linkage is the main problem that we have. So what this does is this causes a cascading change in the rows of 789 and 1101. So all the previous rows generated by 789, 101, or 103 have to be updated with this related ID field, not probably immediately, but at least when we read the data in for processing, we need to understand that this is a change that is happening. So what is the main access pattern that we're trying to solve here, right? I gave you a complex segmentation query that is for fact deactivation. But the primary use case that we're trying to optimize for today is we want to run multiple queries over one single row. What do I mean by that? So since this is Spark conference, let's actually go a bit into the Spark side of things. Now assume that we have this piece of code, right, which generates a data frame. What we do is we take the raw records that we saw in the data frame or table that we saw earlier, and we do a group by of the related IDs. So at this step, what happens? We get a list of related IDs and a sequence of records put together because of the as a result of the group by. Now for every profile or identity, like a merged identity, we have gotten a set of all activities that have occurred for that identity. Now, what we want to do is we want to execute queries, multiple queries, not one, execute multiple queries on top of this record. Why we do this kind of a pattern? The thing is, we have a system, a customized query engine, which is built for high performance use cases like targeting, bidding, and all that stuff, which can take and compile a huge amount of queries, thousands to tens of thousands of queries, and we can run it on top of like individual rows. So we can't do as in for the use case that we want. People right now will be like, hey, why can't you just run SQL queries, with the FAR scheduler on? This doesn't work because even if you have FAR scheduling and say if you have an effective parallelism of 3 queries at a time, 1,000 queries is going to take a long amount of time. You will still be in an effective waterfall model. So this is the hill that we've chosen to die on. So you need to take my word for it that this is the best approach that we found out. So given that this is the problem that we want to solve, right? Let's look into, now we'll park that part of the thing there, and we will dive slightly into the complexities of the data as such. Our data, like I said before, we're using JSON, right? So JSON, we have a hell a lot of nested fields over here. So the nestedness makes schema inference itself an extremely hard thing. The next part is arrays. So we have a large number of arrays. People love arrays. So we need to support them. And then comes the dreaded map type. Now the map type specifically. Now, so what happens is every single time we have such a schema, a nested Harry schema, just representing thousands or tens of thousands of fields in the schema as a Spark struct type takes tons of memory on the driver. So this is a problem that I wish no one else has, but sadly we do have that, and we've benchmarked that, and we see that as a huge bottleneck for the driver and our processing as such. And added to this complexity, every tenant or client has a different schema. Like what do you say? Client A is going to have, say, they might be a retail client. They will have a different schema. Client B could be like a what do you say, a B2B client, and they would have a different schema. So it's not exactly what do you say, we cannot take commonalities out of this. So we need to treat everyone individually. And adding to this, the schema keeps evolving constantly. Fields can get deleted, updated. We do want to, think of a way like, have like a protobuf kind of a way where you have only additions going on, but no subtractions. But in a real life scenario, right, as people are modeling data, bringing in data into the system, evolution happens. So we can't get away from it. So this is a problem that we need to acknowledge and try to solve for. And on top of that, we also have a multi-source problem. What do I mean by multi-source? We have data coming in from various sources, like from streaming sources, from batch sources. So like as soon as you make a click on a website or you push a button on your app, the data starts flowing into the system, right? So it's like instantaneous. So that could be from the streaming thing. The batch could be like the client could be having a huge data processing system, which is generating summarized data and pushing it into the system. So we need to be able to build a system that can handle multiple sources and multiple channels. What kind of scale are we talking about, right? Because whatever problems I've stated right now, if the scale was small enough, I could throw it into Postgres with JSON support and call it a day. I don't need to do anything more. But the problem is, and it's a good problem to have, is the tenants have tens and billions of rows. We have petabytes of data that we need to manage and query on top of. Millions of requests per second peaking across the system. And this flow that I'm talking about triggers multiple downstream applications, segmentation, activation, like email campaigns, push notifications, etc. So what is DeltaLake, right? So this is a Spark conference, so I'm going to assume that a good amount of people know what DeltaLake is. But for people that are not there, so it's a open source project that implements or helps us achieve the lakehouse architecture. On top of the existing the data lake storage systems like S3 and ADBS. Key features, we're not going to go over everything, right? Because this is not a specific Delta Lake talk. The key thing that I want to focus on is the asset transactions. So you get consistent, as in eventually, we get eventually consistent writes on top of the system between various writing systems, even across various clusters. And then we also get a benefit of like the data versioning system. So you can go back to a snapshot of the data, like say 5 versions back. The good thing is it's not trying to reinvent the wheel by creating a new storage format. It uses Parquet and it makes up for the shortcomings of Parquet with its own transaction log. And also the schema enforcement and evolution is a key part. Audit history is also a very good feature that is necessary for a system like ours. But the most important thing, and I've saved it for the last, is the updates and delete support. Now, if you put together what we went over in the initial, the data flow that we're saying, you can see that we need to do a lot of updates. Inserts goes without saying, but we also need to do a lot of updates and deletes to keep the system consistent with the data that's coming in to represent the actual state of an identity or a merged identity. We could currently what we do is we use a hot store, which is extremely expensive in order to get this capability. So if you are trying to support petabytes of data, it's not good cost-wise on the first to be doing all this on a hot store. So that's where the Delta Lake comes into the picture to try to save us from a huge hot store bills. So in practice, right, Delta Lake, how does it look? What does it look like from an API point of view? For everyone who uses Parquet, instead of using dot format of Parquet, we just use dot format of Delta. That's all. That's the major thing. The key point that we are going to be focusing on today, right, is on the updates and so on. So the update workflow has an API like this, where you're able to specify the stage data or the update data, like for example, dot merge of new data as new data, and you can kind of do a join into with the old data that already exists on the Delta Lake. And it gives good paradigms like, okay, when it's matched, do you want to do an update? When it's not matched, do you want to do an insert or do you want to do a no-op? So this makes it a very nice layout of data that is there. The good thing is also it's SQL compatible, so you don't need to worry about, okay, you don't need all the intricacies of the Scala programmatic API. I just want to write SQL. You're good with that too. This is extremely important, when you have multiple consumers in the system, and not everyone needs to be, proficient in Scala or the Scala programmatic API. Now, we went over, DeltaLake, all the niceties of it. But then there is no free lunch over here, right? So we need to still do some work on our end to make sure that the introduction of DeltaLake in our ecosystem is going to help us without creating a new set of problems. And what we noticed was there are a new set of problems. It's not like a magic bullet to wipe everything off, right? So the first one is the concurrency conflicts. So we went over how we have multiple sources, multiple channels trying to write into the profile store at multiple different throughputs as well as frequencies, right? So this diagram, this chart is from the DeltaLake docs, and the key thing to note is the second row, which talks about how the updates, deletes, and merge intos can conflict with other inserts or mutations that are happening at the same time. Delta does use an optimistic concurrency protocol. So the very nature of optimistic concurrency is kind of assumes that the chances of such a collision happening are less. That is, you're modeling for such a situation. But in reality, with multiple writers and coming here with the situation that I described, what we notice in attacks, it does conflict. So most of the times Delta is able to recover. But once your throughput increases, right, the recovery process itself might not work sometimes. So we need to kind of bake it into an architecture instead of trying to just say like, oh, this might work and pray to God. The next one is the column size. This is not a Delta specific one, but then this is more like a Parquet specific thing, right? When an individual column data exceeds 2 GB, we kind of see a degradation in writes or out of memory errors. This is not necessarily a problem that everyone would face. You always get that one whale of a client who decides to do things their way, and you can't blame them for it. They might have a legitimate reason to stuff in some binary for 2 GB, which is necessary for them. The other thing is the update frequency, right? So I was talking about every single writing source has a different throughput and KDA readings. So if you're going to make multiple frequent updates all the time, what happens is it can cause underlying file store metadata issues. Like take S3 or ADLS with Gen 2. The modern file systems, they are pretty resilient, but then you never know when you're going to hit a limit, right? Because it's not about storing petabytes or exabytes of data. Sometimes you might need to store millions of files itself to represent the petabytes of data. So that's where some limits might get hit. And the internal reason why this actually matters is every single transaction that you do on an individual Parquet partition, it causes a copy on write, where Delta has to take the entire partition, make the mutation, and then write it back. So so the more updates that are there and transactions that you're doing, the more rewrites on the HDFS that there can be. So if your underlying file system is expensive for the blocks of writes that you do, you might end up in a very tricky situation. And the other thing is you might end up with too many small files. But Delta does have some things put in place like auto compaction and optimized writes to help us. We're going to look at that in a bit. So our existing change data capture system is you have a bunch of apps that can mutate data, like batch ingestion, streaming ingestion, or an API-based put or a post that can make changes to data. They send requests to the hot store. Once we get an acknowledge back with a 2xx, we emit a CDC message on the fire hose to say like this is a logical change that's happened. So what we want to do here is we want to replicate the data from this hot store into the cold store or the Delta store in order to be able to do scans on top of that for the use case that I mentioned before. So let's look at how this flow will look like. Right? So we we have the familiar table that we saw earlier with the primary ID, related ID, and all the fields residing in the hot store. We have a batch process to backfill data till a time boundary. So we write it to a DeltaLake table. Let's call it the raw table for all facts and purposes from now. A very important distinction between what you see on the left-hand side and the right-hand side is that you see that the primary ID and related ID are maintained, but then all the fields 1 to 1000 and more have disappeared into a column called JSON String. So what we decided to do was we're going to touch into this interesting anti-pattern. A lot of people will be like, wait, what the hell are you doing? This is not how Parquet should be used. But we will actually go into a bit why we are doing this anti-pattern. So that's the biggest and glaring thing that I would focus your attentions on. The other normal flow that we want to do is once you backfill the data, right? You have the change feed notifications expressing the changes coming in. So you get an ID. And we have a long-running Spark structure streaming application, it's called the CDC dumper. It dumps data into a global single tenant, sorry, a multi-tenant staging table. This staging table, the key thing to note, it's append only. And it's partitioned by tenant and by 15-minute time increments. I have a diagram showing what the 15-minute time interval looks like and why. So the key thing to note is this is append only. So we're kind of eliminating the problem that we're talking about, with multiple writers trying to conflict with each other. So you can, in effect, have multiple partitions of the CDC dumper writing to the same, trying to modify the same partition. But since it's an append only, it's not, an insert will not conflict with another insert. So for the high throughput writes, we are taking care of by getting it returned into an append only staging table and solving that issue there. The next thing is we have a long running processor that kind of checks for work every X minutes. It's configurable according to a temp. Now it looks at, hey, do I have any work to do? And it's going to ask the staging table, since the last time I saw you, do I have work to do for a particular tenant? Then if so, give me records back. And then it takes them and it does an upsert and a delete into the individual tenants raw table. So now you see why we needed the upsert and delete functionality into Parquet, which we get from the DeltaLake point of view. And the next question can be like, hey, but you did say that mutations can cause a problem, as in simultaneous mutations can cause an issue, right? So what if the processor and the backfill are running at the same time? So that would be a very likely scenario. And that is why we have a tenant lock put in place on every raw table so that only a single process can actually write into the raw table. So the key difference that we're going to see is we're doing the fan in pattern versus the fan out. The fan out is extremely easy, right? You have multiple different microservices trying to do its own thing. But the problem is you're going to run into cost issues because everyone's trying to do their own thing. You're not going to be able to optimize for cost. So by centralizing all the reads from the change data capture, we have guaranteed that all writes, writes to the hot store generate a seed, CDC. And since the staging table is in an append only mode, we will not have conflicts for it. The next thing is for the size problem that I said, if we end up having some bad data, right, from system enforcements that we need to do, we can filter it out based on thresholds before making it to the raw table in the staging table itself. The next thing is, I was talking about the update key cadence and the frequency of updates. Since we are batching the writes by reading larger blocks of data from the staging table is acting like a message buffer. So we don't have to worry about, okay, we can set SLAs like, okay, in 15 minutes, the data would have been replicated from the hot store to the cold store or the DeltaLake store. So we are able to take care of the two small file problems, at least in the raw table, which is our main source of scan or the mirror or the replica that we are worried about. If you remember, I was talking about the 15-minute time interval partitioning on the staging table. We do this because we get a lot of bursty traffic, right? Suddenly you might have huge traffic in a detail site and so on. So we need a way to kind of bunch the data together, even in the staging table, before even getting to the raw table. So what we do is the staging table is kind of partitioned in 15-minute intervals for every hour. So every hour would have at max 4 intervals. And we keep track of how much progress has been made by the staging tables through the progress map. So this tenant 1 has finished, say, quarter 1 at 9:15 PST or UTC, however you can look at it. So this gives you a logical view of how we are representing data in the staging table, because all the CDC records are partitioned in this fashion. Now comes the big question of why are we using the JSON string format, right? So like I said before, this is an anti-pattern. What we want to do is a schema on read approach. I spent half a slide talking about the problems of the schema evolution and the nestedness and so on. So what we saw was, to begin with, nested schema evolution in 2020, in early 2020, was not supported on an update. So since we do have a good amount of update workload, and Delta did not have it at that time, we were forced to look at other alternatives. It is supported with the latest version though, so that's a good thing. But then we noticed another side effect, because after we took this, what we do is, before we apply changes or patches into, say, the hot store, we have like a stored procedure, which resolves and merges the conflicts between the new data and the old data. Now, how would we do something like this in Spark? The answer would be a UDF. Now, UDFs, like I said, UDFs are very strict on types. So if every tenant has its own schema, and if we have to maintain the evolving schema and the UDFs for that, it is a maintenance nightmare to try to maintain UDFs dynamically for so many tenants. Now we just have one single UDF for the resolve and merge, and it's just a simple JSON merge with our own sprinkling of custom stuff in it. Other thing is, we use JSON iter, which is an extremely fast library. The main thing that it gives us, it does lazy parsing. So unless you're actually using a field, that field is not passed into memory. So which is extremely useful in the cases that we have. The next question that usually people ask me is, hey, don't you lose predicate pushdown? We did pull out all the fields that are necessary for our existing workloads, like timestamp, record type, ID, etc. The rest, we did like a comparison where we read the whole JSON string from the data lake, deserialized it and did processing. And then we also read just 20% of all the fields from hot store all the time, right? The data lake one, like without even a hint of a competition. The schema on read seems to be a much more future-safe approach, at least the way that we are proceeding right now, and seems to be much more manageable from a code point of view and a performance point of view. Any downstream structs that we want to materialize, they will have structs, though, so we don't have to worry too much about that. The partitioning scheme as such of this is very simple. The main thing that I would pay attention to is the Z order on the primary ID, and also the timestamp being used, because sometimes not all data have timestamp. So it will just default to the high default value. The Z ordering definitely helps, specifically on the update part, because we want very quick access to find out which partition a particular an ID is available, so that we can update it. The most important thing with our structure, with the JSON string, is the delta.data skipping num indexed columns. Delta by default tries to generate statistics on every single column that there is, which helps it do effective data skipping while the query planning is happening. But for JSON strings, it's just a massive binary blob. We don't want it to do all that analysis. So it wastes a lot of time in ingestion. So turning it off for that column makes a huge difference in our ingest time. So monitoring the system is also an extremely important thing. So we have two ways to monitor the system. One is the CDC lag from Kafka, that is the upstream. We need to say, we're able to tell how much more work is needed to be done to be right, as in for us to write to the staging table. The second lag is how we track lag on a per tenant basis. Like if I take a tenant, I need to be able to say, okay, how much more time would it take for me to probably have it replicated to the current state it is. So what we do is we have internal data structures tracking the max timestamp in the CDC per tenant. We also track the max timestamp processed by the processor. So we are able to use the difference of this to give a rough lag of replication to say how much work has been done or how much, yeah. So that definitely helps us monitor the health of the system. Now, after talking all of this, right, we need to understand, okay, for your workloads, how did the merge and upset performance do? Because we all know Parquet reads are extremely efficient, but the bread and butter thing that we're talking about, the update and delete, how is that doing? So we simulate, so we took a particular tenant and we kind of analyzed the traffic for them. So how long does it take X CDC messages to get updated or upserted into the raw table that we have? And what we noticed was for 170,000 records, which maps to around 100K records that we need to update into, took just 15 seconds with a very minimal cluster that we have. The second one was 1.7 million CDC records, like changed records, which maps to 1 million rows that we need to upsert into. That just took over a minute. So this is like fantastic with respect to scalability, even for the upsert, to get into the raw table. And this is post the staging table, right? So we have already grouped a good amount of data. So this helps us scale to a good amount of throughput coming from various sources. Two important settings. These are available only in the proprietary version, but extremely important to note is the auto compact and the optimized run. These two make a huge difference in the performance that you get for the insights. Now, the read, right? I was talking about the use case where we need to execute multiple queries. So for that, we took a particular tenant, 1 TB of data on the hot store. It becomes just 64 GB of data on DeltaLake. Of course, with Parquet compression, it's going to happen for sure. The number of partitions on the NoSQL store was just 80. The number of partitions on the DeltaLake is 189. This is extremely useful because you can have a 112 node cluster, 112 core cluster, but you won't be able to utilize the core count efficiently. Now, because of the 189 partitions, we are able to utilize it pretty efficiently. So what we saw is the job time that took went from 3 hours to 25 minutes. For some orgs, for some tenants, it's a massive improvement, even more than what we are showing over here. So takeaways wise, what I would say is the scan IO speed from the data lake is always way greater than the hot store. This is just understating the obvious, but sometimes it just needs to be said. We're able to get reasonably fast, eventually consistent replication within minutes. So by trading off the minute instead of like instantaneous seconds, we are able to reduce the cost by a massive volume. More partitions means better Spark executed code utilization. We just saw that in action in the previous slide. And this also gives us a lot more ability, to aggressively remove data in the hot store. What data do we actually need? Can we remove it more aggressively? The main thing that I would say that came out of this is an incremental computation framework, because the staging table tells you between time T1 to T2, what has changed. So now we have a programmatic way to fetch those changes and make incremental changes or processing on top of it. So hopefully this was useful to you guys. This was DeltaLake has made a huge effect in our workloads. So yeah, I'm hoping to hear some feedback with respect to how it's working for you guys too, or any comments to improve our own workloads are always welcome. Thank you.